In programming languages, a type system is a collection of rules that assign a property called type to various constructs a computer program consists of, such as variables, expressions, functions or modules. The main purpose of a type system is to reduce possibilities for bugs in computer programs by defining interfaces between different parts of a computer program, and then checking that the parts have been connected in a consistent way. This checking can happen statically, dynamically, or as a combination of static and dynamic checking. Type systems have other purposes as well, such as enabling certain compiler optimizations, allowing for multiple dispatch, providing a form of documentation, etc. A type system associates a type with each computed value and, by examining the flow of these values, it attempts to ensure or prove that no type errors can occur. The particular type system in question determines exactly what constitutes a type error, but in general the aim is to prevent operations expecting a certain kind of value from being used with values for which that operation does not make sense. Memory errors will also be prevented. Type systems are often specified as part of programming languages, and built into the interpreters and compilers for them, although the type system of a language can be extended by optional tools that perform additional kinds of checks using the language's original type syntax and grammar. Usage overview. An example of a simple type system is that of the C language. The portions of a C program are the function definitions. One function is invoked by another function. The interface of a function states the name of the function and a list of values that are passed to the function's code. The code of an invoking function states the name of the invoked, along with the names of variables that hold values to pass to it. During execution, the values are placed into temporary storage, then execution jumps to the code of the invoked function. The invoked function's code accesses the values and makes use of them. If the instructions inside the function are written with the assumption of receiving an integer value, but the calling code passed a floating point value, then the wrong result will be computed by the invoked function. If the types do not match, the compiler throws a compile time error. A compiler may also use the static type of a value to optimize the storage it needs and the choice of algorithms for operations on the value. In many C compilers, the float data type, for example, is represented in 32 bits. In accord with the IEEE specification for single precision floating point numbers, they will thus use floating point-specific microprocessor operations on those values. The depth of type constraints and the manner of their evaluation affect the typing of the language. A programming language may further associate an operation with varying concrete algorithms on each type in the case of type polymorphism. Type theory is the study of type systems. Although the concrete type systems of programming languages originate from practical issues of computer architecture, compiler implementation, and language design fundamentals. Formally, type theory studies type systems. A programming language must have occurrence to type check using the type system whether at compile time or runtime, manually annotated or automatically inferred. As Mark Manasseh concisely put it, the fundamental problem addressed by type theory is to ensure that programs have meaning. The fundamental problem caused by a type theory is that meaningful programs may not have meanings ascribed to them. The quest for richer type systems results from this tension. Assigning a data type, typing, gives meaning to a sequences of bits such as a value in memory or some object such as a variable. The hardware of a general-purpose computer is unable to discriminate between, for example, a memory address and an instruction code, or between a character, an integer, or a floating point number, because it makes no intrinsic distinction between any of the possible values that a sequence of bits might mean. Associating a sequence of bits with a type conveys that meaning to the programmable hardware to form a symbolic system composed of that hardware and some program. A program associates each value with at least one particular type, but it also can occur that one value is associated with many subtypes. Other entities, such as objects, modules, communication channels, dependencies can become associated with a type. Even a type can become associated with a type. An implementation of a type system could in theory associate identifications called data type, class, and kind. These are the abstractions that typing can go through, on a hierarchy of levels contained in a system. When a programming language evolves a more elaborate type system, it gains a more finely grained rule set than basic type checking. But this comes at a price when the type inferences become undecidable, and when more attention must be paid by the programmer to annotate code or to consider computer-related operations and functioning. It is challenging to find a sufficiently expressive type system that satisfies all programming practices in a type-safe manner. The more type restrictions that are imposed by the compiler, the more strongly typed a programming language is. Strongly typed languages often require the programmer to make explicit conversions in contexts where an implicit conversion would cause no harm. Pascal's type system has been described as too strong, because, for example, the size of an array or string is part of its type, making some programming tasks difficult. Haskell is also strongly typed, but its types are automatically inferred so that explicit conversions are often unnecessary. A programming language compiler can also implement a dependent type or an effect system, which enables even more program specifications to be verified by a type checker. Beyond simple value type pairs, a virtual region of code is associated with an effect component describing what is being done with what, and enabling, for example, to throw an error report. Thus, the symbolic system may be a type and effect system, which endows it with more safety checking than type checking alone. Whether automated by the compiler or specified by a programmer, a type system makes program behavior illegal that is outside the type system rules. Advantages provided by programmer-specified type systems include abstraction. Types enable programmers to think at a higher level than the bit or byte, not bothering with low-level implementation. For example, programmers can begin to think of a string as a collection of character values instead of as a mere array of bytes. Higher still, types enable programmers to think about and express interfaces between two of any sized subsystems. This enables more levels of localization so that the definitions required for interoperability of the subsystems remain consistent when those two subsystems communicate. Documentation. In more expressive type systems, types can serve as a form of documentation clarifying the intent of the programmer. For instance, if a programmer declares a function as returning a timestamp type, this documents the function when the timestamp type can be explicitly declared deeper in the code to be integer type. Advantages provided by compiler-specified type systems include optimization. Static type checking may provide useful compile time information. For example, if a type requires that a value must align in memory at a multiple of 4 bytes, the compiler may be able to use more efficient machine instructions. Safety. A type system enables the compiler to detect meaningless or probably invalid code. For example, we can identify an expression 3, hello, world, as invalid, when the rules do not specify how to divide an integer by a string. Strong typing offers more safety, but cannot guarantee complete type safety. Type safety contributes to program correctness, but can only guarantee correctness at the expense of making the type checking itself an undecidable problem. In a type system with automated type checking, a program may prove to run incorrectly yet be safely typed, and produce no compiler errors. Division by zero is an unsafe and incorrect operation, but a type checker running only at compile time doesn't scan for division by zero in most programming languages, and then it is left as a runtime error. To prove the absence of these more general than types defects, other kinds of formal methods, collectively known as program analyses, are in common use. Alternatively, a sufficiently expressive type system, such as independently typed languages, can prevent these kinds of errors. In addition, software testing is an empirical method for finding errors that the type checker cannot detect.